Hey there, thanks for clicking this video. My name is Mo from University of Delaware. This is a recorded video for our paper SMIL Multimodal Learning with Severely Missing Modality. This work is directed by my advisor Dr. Qi Peng and done in collaboration with Snap Research and Rutgers University. In this paper, we studied multimodal learning but with severe missing modality. We tackle this problem with two objectives: flexibility and efficiency. We also conduct experiments to evaluate the flexibility and the efficiency of the proposed method. Next, I will talk about the motivation. An assumption made by conventional multimodal learning is that the multimodal data are modality complete. For example, in the multimodal IMDb dataset, each movie poster will have a corresponding text to describe its plot. In the CMU-MOSI dataset, each clip will have associated audio and text modality. However, in real-world scenario, modality complete data are not always available due to all kinds of reasons. One reason could be the private constraints. In social network, we are likely not able to access multi-complete data because the private constraints applied by the users. Another reason could be the budget issues. If your budget is limited, then the 3D point cloud data is hard to obtain because LiDAR is quite expensive. So we believe a real-world multimodal dataset is likely containing both modality complete and incomplete data. Now here comes two questions. What if modality are allowed to be missing in testing, training, and or both? And what if the missing situation is severe? For example, 90% training samples are modality incomplete. Actually, these two questions point out two properties we have to consider. The first one is flexibility. The model should be able to uniformly handle missing modality in training, testing, or both. The second one is efficiency. The learning process of the model should be efficient even under severe missing modality. In this paper, we name our problem multimodal learning with severe missing modality. The left image is the demonstration of our setting using a multimodal dataset with two modalities, image and audio. We're trying to tackle our problem with two objectives, efficiency and flexibility. Flexibility is designed for missing modality in training, testing, or both. Efficiency is proposed for severe missing. There exists some work trying to address flexibility, but most of the efforts mainly focusing on missing modality in testing. The left image gives their setting. They assume all the training samples are modality complete. Well, but testing samples are allowed to be modality complete or incomplete. Their goal is to train a model that can handle missing modality, handle testing with both modality complete and incomplete samples. The key idea is for this setting is mimic missing modality during training. For example, in MFM, they manually mask out some modalities of their training samples and let the model to predict the missing modality using all available modality. During testing, the modality can first estimate the missing modality and conduct multimodal testing. A straightforward solution to tackle efficiency is leverage the generative model-based method. The basic idea is to leverage the modality complete training samples to train a cross-modality transfer model that can conduct cross-modality generation. For example, we can transfer the RGB image to the corresponding audio modality. Once we got the transfer model, and we can use it to impute the modality incomplete samples to be modality complete. But there are some limitations of this solution. First, it requires large number of modality complete samples to train a good generative model. And the second one, it involves pre-training of the generative model. Now, let's look at how we address flexibility. The key challenge of flexibility is tackling missing modality during training. Because once our model can tackle missing modality in training, it will be straightforward for it to handle missing modality in testing. During training, we have two types of samples. For modality complete samples, we handle them same as a conventional multimodal learning. Here, we use the late fusion to get the joint feature. For the modality incomplete samples, we introduce a feature approximation network FAST-C to approximate the feature of the missing modality. We can combine these two frameworks together to get a unified training framework. This unified training framework enables flexible learning using modality complete and incomplete data. Now, let's look at how we address flexibility. The key challenge of flexibility is tackling missing modality during training. Because once our model can tackle missing modality in training, it will be straightforward for it to handle missing modality in testing. During training, we have two types of samples. For modality complete samples, we handle them same as a conventional multimodal learning. Here, we use the late fusion to get the joint feature. For the modality incomplete samples, we introduce a feature approximation network FAST-C to approximate the feature of the missing modality. We can combine these two frameworks together to get a unified training framework. This unified training framework enables flexible learning using modality complete and incomplete data. Okay, now let's look at how we address efficiency. So under severe missing modality, the approximation network will likely lead to a trivial approximation due to lack of modality complete training samples. The trivial expression is usually biased and low quality. So if we directly train it with the trivial approximation feature, this will make our training process less efficient. So to address this issue, we propose a feature regularization network phi-R to regularize the latent feature. This regularization network will enforce the feature to be diverse and maintain relatively high quality. Therefore, the training efficiency can be improved by using the regularized feature. Here is the overall framework. During training, our model leverages both modality complete and incomplete data. During training, the learned model can directly test with found modality and missing modality. We use theta to represent the backbone and phi-C be the approximation network, and phi-R denote the regularization network. Directly train theta and phi separately is not feasible, so we adopt a meta-learning framework to organize the training of all networks. We further split the training dataset into two sub-datasets, a modality complete dataset, DF, containing all modality complete samples, and a modality incomplete dataset, DM, containing all incomplete samples. The entire training scheme consists of three steps: meta-train, meta-test, and meta-update. In meta-train, we use a modality incomplete data. So in order to conduct multimodal learning, we have to first estimate the feature of the missing modality and generate regularization for the latent features. Then we update the backbone using the approximate feature and the regularization. The output of this step is an updated backbone theta star. Next, during meta test, we evaluate the performance of the updated backbone using modality complete data. Finally, we use the calculate the first and second order gradient to update the backbone theta and two auxiliary network in the meta update step. We conduct experiment on 3 datasets. Audio vision AAAI dataset is used for evaluate flexibility, and the CMU-MOSI and the Multimodal MDB dataset are used to evaluate efficiency. So previous method evaluate flexibility by assuming only testing samples can have missing modality. In our paper, both training and testing samples are allowed to be modality incomplete. We evaluate the flexibility on the audio avMNIST dataset. We compare our method with the upper bound, a model trained using 100% image and 100% audio, and the lower bound, a model trained using 100% image, and the two generative model-based method. The reported results of two different settings using a model trained using 100% and some percent audio, like 20% audio. We can see that the generative model-based method cannot handle testing with missing modality because its performance is even worse than the baseline method. However, SMIL demonstrates good flexibility. It performs better than both lower bound and the generative model-based method when testing with modality complete and modality complete samples or modality incomplete samples. This is a result for efficiency. We first look at on the CMU-MOSI dataset. Here, the 20% in this table means the training samples consist of 100% image and 20% text. From the table, we can see that SMIL is efficient on the severe missing modality. In the 20% case, it outperforms the two generative model-based method by 5%, and the improvement increased to 7.5% on the more severe setting, the 10% test case. We also know that multimodal learning is better than single modality learning. We can see that using only additional 10% text, our model outperformed the baseline model quite a lot. We also verify the efficiency on the Multimodal MDB dataset and observe the improvements are consistent on this dataset. SMIL get larger performance gain on their more severe case, and multimodal learning is better than single modality learning. Here is the result. We also visualize the embedding and conduct an ablation study on the multimodal MDB dataset. The left image verifies the effectiveness of our method because our method using only 20% text modality, and it generated an embedding pretty similar to the upper bound, a model trained using 100% text. And we also see that multimodal learning is clearly better than single modality training. From the ablation study, we found that feature regularization is critical for severe missing modality because In a more severe case, without regularization, the performance of model will drop more. All right, here's the summary of our paper, and our code will be available using this link. Thanks for watching.